So now we look at reactions of aromatic compounds. Reactions of aromatic compounds are different than a lot of other functional groups because, as we talked about in the last section, benzene rings are so stable. And because benzene rings are so stable, it's much harder to get them to react, under any set of conditions. So the primary reaction that we look at that deals with substitution on aromatic rings is what we call electrophilic aromatic substitution. And under this category, we're going to look at 5 different reactions. We've got halogenation, nitration, sulfonylation, alkylation, and acylation. And so 2 of these reactions, the bottom 2, are going to let us put carbon groups on there, while the others will allow us to form halogens, nitro groups, and sulfur groups. Now, while this is a variety of different groups that we're going to be substituting on here, all of these reactions consist of the same 3 basic steps. Formation of a good electrophile, nucleophilic attack of the aromatic ring, and proton removal to regain aromaticity. So we're going to go through this once to start in sort of a generic state, and after that we'll look at it in much more specific situations. So the first step is generation of the electrophile. Generally, these reactions require much more reactive electrophiles than other reactions we studied. And that's because, this first step, after this, we're going to get a nucleophilic attack of the aromatic ring. Well, the aromatic ring is a very mediocre to weak nucleophile. And so if we can't make that into a better nucleophile, then our only other option is to have a good electrophile. And so typically the types of electrophiles that we use are ones that we have to make as part of running the reaction. Though typically these electrophiles are too reactive to just have sitting around waiting for us. But we have some X group bonded to our electrophile, and then we add something which is often an acid, and it will help to break or to weaken that bond, and we get a partially positive or sometimes a fully positively charged electrophile. And that's going to encourage our aromatic ring to be able to react as a nucleophile. So that's step 2, nucleophilic attack. And in this step, the pi electrons of the aromatic ring will attack the electrophile. Now this step is almost always rate determining in an electrophilic aromatic substitution reaction. And the reason for that is we're going from an aromatic ring, which we know is highly stabilizing, and in this step we're actually breaking aromaticity and forming a ring that's not aromatic. So that's a step that requires an input of energy. Now this intermediate is resonance stabilized, and we call this combination of resonance structures here the sigma complex. So once we've done that, we just have one more step to do. That third step is usually a very easy step, and that's removing a proton. Why is this step so much easier? Well, this step where we remove a proton regains aromaticity. So we're going to say just B for generic base here. In each of the future examples, we'll define what that base is, but it removes that hydrogen, electrons shift down, and we get our aromatic ring back. So the net result of this reaction is that we've taken a hydrogen on our aromatic ring, and over a couple of mechanistic steps, we've replaced it with some sort of electrophile. So now we can start looking more specifically at some of these reactions. And the first one we're going to look at is the halogenation. And while we label this as halogenation, realistically, this is for bromine or chlorine. This reaction does not work well for iodine. Iodine is not reactive enough, and doesn't work for fluorine either, because fluorine is too reactive. But after we show sort of this basic mechanism for halogenation with bromine and chlorine, we'll show some alternative conditions that can be used for iodine or for fluorine. So the overall reaction is that we take bromine, and this can also work with chlorine, and then in this case we're going to use iron bromide, which is a Lewis acid. Although you can use other acids in this reaction, but the key is that you need a Lewis acid, and that will result in the replacement of one of the hydrogens with a bromine. And this can be a very useful reaction, because once you've put a bromine on there, now this allows you to do all sorts of other reactions, such as adding magnesium, and you can easily make Grignards at this point. All right, how does this work mechanistically? Well, again, remember, we're dealing with this sequence of 3 steps. First step is we're going to have the bromine react with the iron bromide and make an electrophile. And this is actually a fairly straightforward step. The electrons in that bromine-bromine bond will donate their electrons over to the iron, and it doesn't fully make that bromine-bromine bond break, but you can see here it's partially broken, and the bromine iron bond on the other side is partially formed. What we end up with is partial positive here, partial negative on the iron, and this intermediate that we formed, it's not a bromine cation, but it's going to act as if it is one. And so now we've made a better electrophile, and we've made an electrophile that's good enough to react with an aromatic ring. So step B is our nucleophilic attack. Aromatic ring attacks the bromine that's partially positive, and at this point, now that bromine-bromine bond fully breaks. and that leads to the formation of our sigma complex. From here, it's just a matter of that sigma complex getting deprotonated to form our product. The only question might be is, what is the base that's going to initiate that process? Well, because this step is so favorable, it's regaining aromaticity, we don't need a strong base. And so that iron bromide, which became FeBr4-, that negative charge is sufficient to function as the base here. So that grabs our hydrogen, we can shift our electrons down, and we form our product. Now you'll also notice here, as a byproduct, we reform the iron bromide. So that tells us that this species is catalytic in the reaction, and then we get HBr as a byproduct. Now, how does chlorine work? Well, if you want the mechanism, we'll look at the reaction. But it's essentially the same, except instead of bromine, we use chlorine. Instead of iron bromide, we use iron chloride. And the result is that instead of replacing a hydrogen with bromine, we replace it with a chlorine. And we can say here that if we want the mechanism, all you need to do is go back to the previous 2 pages, where this one and the previous one, where we have bromine. Everywhere that we put bromine, put in a chlorine. And the mechanism is exactly the same. Now, what about iodine and fluorine? What do we do in those cases? How do we get them to react? So in the case of iodine, we need a different acid. And so in the case of iodine, if instead of iron bromide you use nitric acid in the presence of iodine, you can put an iodine on your aromatic ring. And fluorine has a very unusual reagent. Yes, that is Xe for xenon, or xenon difluoride. The biggest problem with xenon difluoride is it's very expensive, but you can use that to directly attach a fluorine to an aromatic ring. Now for these two especially, later on in this chapter we will show some better methods, but you can use these if you need to directly iodinate or fluorinate your aromatic ring.